strong bases and weak acid titration. As we can see in this graph, there is an increase in slope, and then all of a sudden it hits this plateau. Okay, so there's a little hump delay, and then after that it slowly goes back up into its increase in slope again, and then eventually hits that equivalence point. Okay, unlike in the previous video where we looked at a strong acid and a strong base as written over here, we've seen that there's no hump. It just slowly goes up until it hits that equivalence point, and of course the equivalence point here is at a pH of 7. Difference here is we have that buffer region over here, which we'll explain shortly, and of course the equivalence point over here is above a 7. Okay, so the equivalence point is higher than in the previous video. Okay, so what is this buffer region? Okay, so there's equal amounts of the acid and its conjugate base. Let's illustrate that in this example over here. This is an acid. Of course, this one then becomes its conjugate base. This is a base, so this becomes its conjugate acid. Of course, this H plus wants to go towards the hydroxide, okay, because it wants to be donated. It's an acid, okay? It drives the reaction towards the right. Why? Because if you have more of this over here, when we add more base in, let's say we added this base from a strong base, okay, then of course it's going to increase over here. It's going to alleviate the stress. It's going to go towards the right. Okay, obviously this is based on Le Chatelier's principle. However, this process can stall. Okay, hence why we have the buffer region, since if an acid is weak, its conjugate base is strong. Acetic acid is a weak acid, so this here is going to become strong. Okay, so this is going to want to accept any protons. If this accepts a proton from this H2O, what's it going to become? This is then going to become C3COH, which is acetic acid, which is acidic. So of course, it's going to want to stop this pH from increasing upwards. Basic, it's going to wants to keep it as acidic, hence why you see this plateau. Okay, in order to continue to go towards the equivalence point, the only thing to do is add more base, and eventually it's going to hit that equivalence point where the concentration of the base is going to equal the concentration of the acid. What is the pH of the solution after the base has been added? Okay, so obviously we're going to be titrating this HCN with this KOH. Okay, so KOH is going to go in towards the HCN. Obviously this one is going to be in lesser amount, so this is all going to be used up. This one is more, so this is going to be left over. Okay, so I'm going to write this down in the change. 8 times 10 to the negative 4. This is how much we have left over of the HCN. All of the KOH has been used up and reacted, and then this is how much is reacted at the very end. Okay, so obviously this is all in moles, so I want to divide by liters. Okay, the liters I'm going to use is obviously putting both of these solutions together, hence why they're in the same beaker, hence why there's going to be a volume. So I'm going to just divide these by volumes, and then eventually going to have this concentration for HCN and this concentration for the KOH. Okay, I'm going to be using this one. This is the acid route. Okay, this one here is the base route. I don't want to be using this one because I have more HCN compared to my base, okay, left over, so I'm going to be using this acid route. So I want to only use this one. So I'm going to be putting our Ka, where our products, these ones, on the top, and then our reactants, the reactant on the bottom. I plug in my values, I end up getting this H3O concentration. I plug it into my pH formula, I end up getting a pH of 8.49. This is the answer. Okay, so I always use this one over here, which one I have more of, the HCN. So if I'm going to use the acid route, I want to use this one. If I have more of the base, I'm going to use this one.